Imagine a whole coaching class. For every student, you jot down to numbers how many hours they study each week and the marks they score on a test. Plot each student as a single dot, and straightaway a shape appears. Students who study more tend to sit higher up. The cloud drifts upward. We want just one number that captures this. How strongly and in which direction do the two quantities move together? That number is the covariance. Scale it to sit neatly between -1 and 1, and it becomes the correlation. Before any formula, hold three pictures in your head. Three little scatter clouds, side by side. When the dots rise from left to right, the covariance is positive. When they fall from left to right, it's negative. And when the cloud has no tilt at all, the covariance is near zero. Here is the key idea underneath both. Take that upward drifting cloud and mark the average study time and the average marks. Draw a vertical line at the mean of x and a horizontal line at the mean of y. These two lines split the plane into 4 quadrants, meeting at the center of the data. Now the trick. In the upper right, a point is above average in both deviations positive, so their product is positive. In the lower left, both are below average. Negative times negative is positive again. Those two quadrants push the score up, but the other two quadrants, above average in one, below in the other, give a negative product, and they push the score down. Covariance simply adds up all these sign products and averages them. So here it is in symbols. The covariance of x and y is the expected value, the long-run average, of x minus its mean times y minus its mean. Read it piece by piece. This factor is how far x sits from its own average. This one, how far y sits from its average. Multiply them, then average that product over the whole population. The sign is the whole point. Positive means they rise together. Negative means one rises as the other falls. And zero means no linear movement at all. Expanding that bracket gives an equivalent form that is far easier to compute with. Covariance equals the expected value of the product xy minus the product of the two separate means. This is the version you'll actually reach for. Find the average of x times y. Find each mean on its own and subtract. And a lovely special case hides inside it. Let y just be x itself. Then covariance of x with x becomes e of x squared minus the mean squared, which is exactly the variance. Variance is nothing but a variable's covariance with itself. There's one snag with covariance. Its size depends on the units. Measure marks out of 10 instead of 100, and the covariance shrinks tenfold, even though the relationship is identical. The number is hard to read on its own, so we normalize. The correlation coefficient, written rho, is the covariance divided by the two standard deviations, sigma x and sigma y. Dividing away the units squeezes the answer into a fixed, unit-free scale. Rho always lands between -1 and 1, no matter what you measured. And the endpoints have crisp meanings. Rho equal to +1 is a perfect increasing straight line. -1 is a perfect decreasing line. And rho equal to 0 means no linear relationship. The strength of the tilt is what rho really measures. Let's compute one all the way through. 5 students. Their study hours are 1 through 5. And their marks are 3, 4, 5, 7, 6. Each student is equally likely, so every point carries weight 1/5. First, the two means. The study hours add to 15 over 5, so the mean of x is 3. The marks add to 25 over 5, so the mean of y is 5. Now for each point, measure its two deviations, how far from the mean in x and how far in y, and multiply them. Here is the cloud, with the mean lines crossing at 3, 5, point by point. The first student is to below in study hours and to below in marks. minus 2 times minus 2 is plus 4. The next, minus 1 and minus 1 gives plus 1. The middle student sits dead on both means, 0. The fourth is 1 above and 2 above, plus 2. The last, 2 above and 1 above, plus 2 again. Every product came out positive or 0. The cloud leans one way, so the deviations agree in sign. Add them up. 4 plus 1 plus 0 plus 2 is 9. Average that sum of 9 over the 5 students, and the covariance is 1.8. Positive, just as the upward cloud promised. For correlation, we also need the two spreads. The squared x deviations are 4, 1, 0, 1, 4, summing to 10. So the variance of x is 2, and sigma x is root 2. The y deviations happen to square to the very same 10, so sigma y is also root 2. Now assemble rho. Covariance 1.8 over root 2 times root 2. And root 2 times root 2 is just 2. So rho is 1.8 over 2, which is 0.9. A strong, positive, nearly linear relationship, comfortably inside minus 1 to 1, exactly as it must be. Let's see the shortcut formula shine when the outcomes carry unequal probabilities. A student is one of two types. Type 1 studies 1 hour and scores 50, with probability 0.4. Type 2 studies 3 hours and scores 90, with probability 0.6. Weight each outcome by its probability. The mean of x is 1 times 0.4 plus 3 times 0.6, which is 2.2. The mean of y is 50 times 0.4 plus 90 times 0.6. That's 74. For the product xy, the first type gives 1 times 50-50. The second gives 3 times 90, 270. Weighted, that's 20 plus 162, 182. Now the shortcut. Covariance is E of xy, 182, minus E of x times E of y. 2.2 times 74 is 162.8. Subtract, and the covariance is 19.2. Covariance also settles a question people get wrong constantly: the variance of a sum. It is not just the two variances added. There's a cross term. The variance of x plus y equals variance of x, plus variance of y, plus twice the covariance. For our two types, the variance of x works out 2.96 and the variance of y to 384. The covariance we just found is 19.2. Plug them in. BFO.ORE 7.96 plus 384 plus twice 19.2. That's twice 19.2, 38.4. Gives 423.36. Drop the cross term and you'd get the wrong answer entirely. Only when the covariance is 0. For instance, when x and y are independent, does variance of a sum collapse back to just the sum of variances? One careful warning though. Independence forces covariance to 0, but the reverse is not guaranteed. A covariance of 0 only rules out a linear link, not every possible dependence. One closely related tool worth meeting: the law of total expectation. When a quantity depends on some condition, average it inside each group first, then take a probability-weighted average of those group means. Picture a machine. On a good day, probability 0.7, it makes 0 defects with chance 0.6 or 1 defect with chance 0.4. On a bad day, probability 0.3, it makes 1 or 2 defects, each with chance 1/2. Inside the good group, the expected defects are 0 times 0.6 plus 1 times 0.4, 0.4. Inside the bad group, 1 and 2 each with 1/2 average to 1.5. Now weight the two group means by how often each day occurs. 0.4 times 0.7 plus 1.5 times 0.3. That's 0.28 plus 0.45, giving 0.73 defects on an average day. Your turn. Here are 4 points, and this time the cloud falls. Study hours 1 to 4, mark 6. 5, 3, 2. Pause the video and find the covariance and the correlation yourself before I do. Here's the walkthrough. The mean of x is 10 over 4, 2.5. The mean of y is 16 over 4, 4. The four signed products come out minus 3, minus a half, minus a half, minus 3. All negative because the cloud descends. They sum to minus 7. So the covariance is minus 1.75. The variance of x is 1.25 and the variance of y is 2.5. So rho is minus 1.75 over the root of their product, which is about minus 0.99. Strong, negative, almost a perfect line. If you landed there, you have genuinely got this. Trap 1. Dropping the product of the means. Covariance is E of xy minus E of x times E of y. Never just E of xy on its own. Trap 2. Accepting an impossible correlation. Rho can never leave minus 1 to 1. If your answer spills past that, there's an arithmetic mistake. Go back and check. Trap 3. Reading zero covariance as independence. It only means no linear relationship. A perfect U-shape can have zero covariance yet be tightly dependent. And trap 4. Forgetting the cross term in the variance of a sum. That plus 2 covariance is not optional. It's only 0 when the covariance itself is 0. Let's lock it in. Covariance measures raw comovement, E of xy minus the product of the means. Its sign tells you the direction. Correlation is covariance normalized by the two standard deviations. It's unit-free, always between minus 1 and 1, and it measures the strength of a linear relationship. And whenever you add to random variables, remember the cross term. Master these three lines, and covariance and correlation will never trip you up again.